All right, good afternoon, class. So today our goal is going to be covering 2.2a and 2.2b of our textbook. But before we do that, I'd like to just quickly go over some last minute things on 2.1b that we ran out of time for on the last video. So we're going to go ahead and start there, and then we'll move on to 2.2, cover the new material, and go from there. So let's go ahead and get started. Just as a refresher, so we were talking about 2.1b last time, and we were discussing how we have these left-hand limits, so x can approach t from the left for some f of x function, and if that's equal to L, and then if we're looking at the right-hand function, or the right-hand limit I mean, as we approach t from the right, if that also equals L, if we have this, then the limit as x goes to t for f of x is also equal to L. And this statement goes both directions. If you have this, then it also implies that. So we talked about that. That's not anything new. What we did not get a chance to cover just yet was some of these special cases about when it does not exist. We did talk about if the limit as x approaches t from the left of f of x does not equal the limit as x approaches t from the right, then in this case, the actual limit does not exist. But there are a few other cases that we should probably discuss, just that when you encounter them in your practice and your homework, that these things won't catch you off guard when you see them. The other case is, suppose we're dealing with a fraction, and the question asks about the limit as x goes to t, and suppose the fraction can be written as some function of x divided by some other function of g on your denominator. In this case, now in general when we're talking about limits, you want to try to plug in t first to see if you'll be able to find your answer that way. So when you plug in t for the numerator and denominator, if the numerator, which in this case is f of x, does not go to 0, but the denominator, which in this case is g of x, does go to 0. So we have a case where if I try to plug in t, then I'm getting some other number in the numerator that is not 0 and a 0 in the denominator. Then in this case, whenever this happens, you can go ahead and know that the limit does not exist. Sometimes that can save you the headache of trying to find some clever way of simplifying it further. In many cases, especially when this happens, there's nothing you're going to be able to do to fix it. It just doesn't exist. Case in point, we talked about last class, I believe, this function f of x is equal to x plus 2 divided by x minus 1. Now there's no clever tricks we can use to simplify this, but if I try to take the limit of this as x goes to 1 for f of x, then I'm going to have 3 divided by 0, which obviously we can't do that, can't divide by 0, so this limit does not exist. And this makes sense because if you remember the graph for this one, we had the vertical asymptote at 1, and we had a horizontal asymptote also at 1, divide their coefficients. And our graph looked something like this. So from the left side, as we approach this x equals 1 line, or I'm sorry, that's x equals 1. As we approach this x equals 1 line, from the left side it's going to positive infinity, from the right side it's going to negative infinity, and obviously positive infinity does not equal negative infinity. The left hand and right hand limits do not equal each other, and so the limit does not exist. So we can see that graphically, but in order to save the time of having to graph it, if you just look at the fraction, and you see that when you plug in your numbers, you're getting a number divided by a 0, then it does not exist. So keep that in mind as we move forward. So the last thing, well, two more things I want to talk about in 2.1b. The next thing we want to discuss is, okay, so obviously in this case it doesn't exist because one's going to positive infinity, one's going to negative infinity, but so what? What if they're both going in the same direction? What if they both go to positive infinity? Well, that's where, and this will actually vary. Sometimes in different math classes, different professors may define it differently. However, for the purposes of this class, and in general, what's usually done is that we say if the limit from the left for f of x from the left is equal to the limit as x approaches t from the right of f of x, and if they both equal the same sign, so they're both positive infinity, right? Well, that tells us the limit as x goes to t of f of x is positive infinity. But in this case, we say, and give me just one moment. All right, apologize for the interruption, though I guess from your perspective, nothing really changed too much. At any rate, back to what we're talking about. Right, so the left hand and right hand limit agree. They both go to infinity in the same direction. They both go to positive infinity. Then the limit goes to positive infinity. But we say the limit when it goes to positive infinity, we say that in this case it does not exist. Why do we say that? Well, by our definition for the limit over here, we said that the limit existed when the left hand and right hand limits both agreed on the same value of L, where L is some real number. So positive infinity, while yes, I mean abstractly we do think of it as a number, it's not a real number, not like 1 or 5 or 20 or 30 or whatever. And so by this definition, because positive infinity, it's not a possible L, since L has to be some real number, then we say the limit does not exist. And the same is true as if you get negative infinity, then we also say it does not exist. An example of that, if you consider the function absolute value of 1 over x, then this graph is going to look something like this here. And a bit of a sloppy drawing, but you get the idea. As this function is approaching 0, from both in the left and right sides, the function is going to positive infinity, and so we say the limit does not exist. Another way to think about this is that when we look at it graphically, we say the limit doesn't exist because, well, what is the function at x equals 0, at this point? Well, we don't have any point here where these two lines from the left and right actually connect on this graph, because they connect, well, theoretically at infinity. So we consider the limit to not exist. So keep that in mind. Let's see. Those were the cases I wanted to talk about. for when the limit does not exist. The last vocabulary term that we need to cover for 2.1b so let's see, let me organize here. We had our definition. We had if they're not equal to each other, it doesn't exist. And then we have our rule down here that if the numerator is a number but the denominator is 0, then it does not exist. Our last vocabulary term deals with if we have a limit of the form, so the limit as x goes to t of f of x, where f of x is some function that's g of x divided by h of x. So this is like our example of, again, having a fraction for our function that we're evaluating the numerator for. In the case where this happens, then if let me make sure I get this written correctly. Yeah, okay. If the limit for the numerator as x goes to t, so this is of g of x, is equal to 0, and the limit as x goes to t for h of x, for our denominator, is also equal to 0, so we have a 0 divided by 0, then we call this limit indeterminate. Which basically just means that in its current form, we can't say anything about what the limit is. It could exist. It could be that it doesn't exist. In the case of our example over here with this fraction, we had a number divided by a 0, so we knew it does not exist. But here, if we have a 0 divided by 0, well, it's inconclusive. We can't say anything about it. So what do you do from here? Well, you've got a few options. You could try maybe factoring the numerator or denominator, try to simplify it into a form where you can plug in the numbers. So simplify, factor it. And if that's still not working, you're not really sure what to do, as a last resort, you really can't go wrong with just graphing it. Well, yeah, graphing it. When you can look at it on paper, or we can look at it on a graphing calculator or on Desmos or whatever it is you use, you can see what it looks like. You can see where is the function going as it approaches some point, and that's going to help you get some kind of clue as to what's going on here. So use your resources, and just because you have a 0 divided by a 0 for a fraction, that doesn't necessarily mean anything. So don't assume it doesn't exist just because you have 0 divided by 0. That just means it's indeterminate, and in that case, take the extra time to work through it a little bit and try to force the answer to come out of it somehow. So those were the last few things I wanted to talk about for 2.1b. So, yeah. Let's go ahead and move on to 2.2. We're going to get our first introduction to derivatives. So now we're starting to get at the heart of calculus, trying to find our slopes. We've already talked some about what slope is, rise over run, change in y divided by change in x. We've also talked about limits now, and so we can start to examine the limit definition for the derivative. But that will come in 2.2b. So now for today's portion of the lesson, we want to look at section 2.2a. And here, so let's just refresh our memories on some vocabulary we've already covered in some previous lectures. We already know that delta x, this is change in x, and delta y, this is change in y. So far so good, nothing new there. Right, so for a given function, y equals f of x, and I have it written like this just because oftentimes, as an example, we see functions written as like y equals, I don't know, 2x plus 3. But we could also write this as f of x equals 2x plus 3. In either case, y is your f of x value. So y is our f of x, and so as x changes from x1 to x2, then y changes from y1 to y2. Now remember, this is a function, so this y1 is actually a result of what you get when you plug in x1. So y1 is equivalent to f of x1, and y2 is equivalent to f of x2. So we have this idea of change between x is impacting some change in y, or in other words, if we have a point from x1, y1 on our graph, and this point is changing to x2, y2, then we can create this kind of relationship between two different points on the same graph. So what do I mean by that? Why do we care? Well, this is where we get the definition for the average rate of change. Average rate of change. Now, what is the rate of change? Well, we've already discussed before that we think of slope as delta y divided by delta x. So if I look at the change in y divided by change in x, in other words, the rise divided by run for slope, then the average rate of change between these 2 points is just the difference. So y2 minus y1, that's the change in our y. x2 minus x1, change in our x's, but our y's we can rewrite as f of x2 minus f of x1. And this is what we call average rate of change. Or in other words, you have a graph here, and it does, I don't know, something like that. Then you take some point on it. This is x1, y1. And then you take some other point on it. This is x2, y2. Then this line between it also has a slope. But this slope, more specifically, we call the average rate of change. It's the average change between these 2 points, which is this delta y divided by delta x formula here. So that's what it looks like graphically when we're doing this, and that's the slope for this dotted line that we're calculating here. So that's average rate of change. That's how it looks on a graph. For the sake of demonstrations later, I'm actually going to leave this picture here because we need that in 2.2b. But before we move on to 2.2b, let me just handle a couple other examples real quick, and then we'll move on. So change in y, change in x, and average rate of change. Remember this formula? You're going to need this, especially if during your homework or your quizzes on Hawks Learning, they may ask you specifically, what is the average rate of change for a given point in this given function? This is the formula you're going to need for that. So keep that in mind. But we'll work through an example or two just so you can see what that looks like. And then you should be good to go for the homeworks. All right. So for our first example, we have f of x is equal to, let me make sure I copy this correctly, 3x squared minus 2x minus 1. And we're curious about from x1 equals 1 to x2 equals 1.5. What is the rate of change? So this is a question you may very likely see on Hawks Learning. So we're just going to apply our formula here. We know it's delta y divided by delta x, or in other words, f of x2 minus f of x1 divided by x2 minus x1. So I'm just going to plug it in. x2 is 1.5, so I'm going to write that in. 3 times 1.5 squared minus 2 times 1.5 minus 1. And then what I get when I plug in 1, but make sure you distribute this negative here when you write it out with this function. So we're going to have minus 3 times 1 squared plus 2 times 1 plus 1. And this is all divided by 1.5 minus 1. So far all I've done is just copy and paste these numbers from this formula based on this equation that I'm given. If you get to this step and you can do this step correctly, you're already halfway done. All you have left to do now is just, you can plug in the numbers in the calculator if you're not confident about it, but now it's just a matter of arithmetic, adding these numbers up together correctly. So start with the numerator, and for the numerator, you're going to get 2.75, and for the denominator, 1.5 minus 1, you're going to get 0.5. And 2.75 divided by 0.5, that's going to give you 5.5. So that is the average rate of change from x1 to x2. And there you have it. So that's what average rate of change is. That's how you can calculate it. You may see some questions specifically asking you for it in the Hawks Learning section for 2.2a. But more specifically, we care about the average rate of change because it's a nice little introduction for what is the derivative. And that we're going to be discussing in 2.2b. So let's go ahead and switch gears. I'm going to leave this picture up here because we're going to need this here in a few moments. All right, so 2.2b. Again, this is an introduction to derivatives now, using the limit definition for a derivative. So 2.2b. Right. So we already have our idea for average rate of change. This is delta y divided by delta x. But more specifically, let's suppose we're dealing with some more real-world kind of examples. Maybe you have a runner, and given a particular time, I'm going to call that t, we then know how far this runner has ran, what distance he has covered. So I'm going to call that d. So here, t is our x, y is our d. That in this example, for a runner that's covering some amount of distance over a time t, then the average rate of change is delta d divided by delta t. Now, why do we care about this? Why do I bring this up? Well, because in these real-world examples and in these physics examples, what is change in distance? Well, you can think of that as velocity, or a speed. It's your change, how much distance you're covering, over an amount of time. But what is, well, I misspoke here. Change in d is just our change in distance, so it's distance covered. And what is a distance divided by time? Well, that is actually what our velocity is. This is our speed. Because if you think about it, like when you're driving your car, it's in miles per hour. That's a distance, miles, divided by time, hour. It's a velocity. This is a speed. So in other words, delta t divided by delta t is the average rate of velocity. It's your, well, not average rate of velocity, it's your average velocity. So this is average velocity. Okay, so that's all fine and good, but why do we care about average velocity? I mean, if we're looking at a race or what have you, we can get an average for how fast somebody was going, but we don't care about on average how fast they were going. We would like to know what was their top speed, what was their slowest speed at time equals 5 seconds, how fast were they running? We would like to know more specific information about the velocity rather than just the average. So what I'm describing there is when we're trying to find out what was the speed at time equals 1, or what was the speed at time equals 0, how fast did he start when he launched himself from the starting point, or herself. That, instead of an average, is what we call, oops, let me get my eraser. That is what we call instantaneous velocity. So we have this example up here of what average velocity is. However, when you take the same formula, when you have delta d, delta t, this is our average velocity here, but if we take the limit as delta t goes to 0, this gives us the instantaneous velocity that we're looking for. So why do I say delta t goes to 0? Well, in the case of an average velocity or an average rate of change, we're looking at dividing by, what was the speed at time equals 1 versus what was the speed at time equals 2? What was the average there? Whereas here, we're not talking about multiple points. I just want to know how fast was he going at this single point. So in order to get a rate of change at a particular point, then the amount of change along the x-axis has to approach 0, right? Because if you think about it on a graph, if I have some function here, and I want to know the slope at x equals 1, or the instantaneous velocity at x equals 1, then I'm just looking at this particular point, and this change in the x-axis, this change in t, well, with only one point, there is no change, and so that is 0. So don't let that scare you too much just yet. Obviously, we can't just, oops, that should be an arrow. We can't just plug in 0 here, because then we would divide by 0, and that's bad. We can't do that. But, just as we discussed for 2.1b, when you're dealing with these limits and you have these cases where you have a 0 in the denominator, there are steps we can take to simplify it so that we can actually get the answer we're looking for. And you'll see examples of that. But before we get there, there's a few other definitions we want to cover. So that's instantaneous velocity as delta t goes to 0. Or in other words, if you want to switch back to y and x, then this is the limit as delta y divided by, oops, not dx, delta x. Divided by delta x as delta x goes to 0. This is also called the instantaneous rate of change. So instantaneous rate of change, instantaneous velocity, these are really the same thing. The only difference in the vocabulary here is that if you're dealing with an application where we're talking about speed, we're talking about velocity, then that's what it is that we have here. Whereas in general, if it isn't a particular application or we're just using general y and x, then it's just a rate of change because we don't know if it's velocity or some other vocabulary term. At any rate, these two are the same ideas. So we have this idea of instantaneous rate of change at a particular moment when this delta t, the change in t, or your change in x is going to 0. And we're trying to find the slope at a particular point when t equals some particular a value. That could be 1, 2, 3, what have you. So, what we're really describing here is slope. And I think in a previous section we already talked about what slope is, but slope is delta y divided by delta x. It's your change in y, which is rise, divided by your change in x, which is your run. So slope is your change in y divided by change in x. When we talk about this instantaneous rate of change, what we're really talking about is what is the slope at a particular point. So how is that going to work out? Well, we have some other definitions to more clearly describe which slope we're talking about. In the case of this guy from this drawing that I have from before, we had this average rate of change, this average slope between this point, x1, y1, and this other point, x2, y2, and we could draw this line. This line I have drawn here is called the secant line. Now, I'm not exactly sure if that's a vocabulary term you're going to have to remember, but it very well could be that during your Hawks learning, there may be a certified question that asks, what is the secant line? Or it'll ask, find the secant line of these 2 points. Well, this is what a secant line is. So this line is called the secant line between two given points, between x1, y1, and x2, y2, and has a slope equal to the average rate of change. So remember that formula we had from before for the average rate of change. You can use that formula with these 2 points to find the slope the average rate of change between the 2 points? Well, if you want to find the equation for that line, you now have the slope, you now have a point, then use the point-slope form equation for a line, which I think we've talked about before, but just as a refresher, y minus y1 is equal to m times x minus x1, where y1 and x1 is some particular point. So use this equation, find your slope, take either of these points, whichever one you prefer, plug it into this equation, and that's going to give you the equation for this secant line. So that's what a secant line is. That's one of our definition terms. And then the last vocabulary term for this section, we've talked about the secant line, but now we'd like to discuss the tangent line. So the tangent line is the line containing a point from your graph and this line is with a slope equal to the instantaneous rate of change. So notice that this tangent line, it only requires 1 point, not 2, like the secant line. That's because this slope here, instead of calculated using the average rate of change, it's using the instantaneous. So you have your delta x in the denominator going to 0, and we have a limit there to find your derivative, or to find your slope. And so to go back to this picture here, well, if I were to draw the tangent line for, say, this point on the right side, then in reality, looking like it's pretty steep there, that's probably going to be something like this. It's going to be a pretty steep line. Point being, it has the slope, or the steepness, at that particular point, and it also passes through that point. So that's the tangent line here. So tangent line. So that's the tangent line. And so now we've already discussed that the slope, or the instantaneous rate of change, give you a second to write that, copy that if you're wanting to. We've already discussed that the instantaneous rate of change is the limit. It is the limit as delta x goes to 0 of delta y divided by delta x. But what does that actually look like? Well, that actually looks like where, oops, not that, where our delta y, this is our change in the y values, or the change in the x's. But we can also say this change in x here, let's call it h for a moment, and say it goes to 0. We're trying to get this h to go to 0. So our denominator, we have h going to 0. But for our y's, what's our change in y's? Well, one value for our y value, we could have an f of x, or we have the amount of change, x plus h. Now, this change is going to 0, so this f of x plus h is just going closer and closer to f of x, but For h values that are not 0, this is some new different y value. That's our change in y minus f of x there. So this is our limit definition for the slope, for the instantaneous rate of change, or in other words, the derivative, which we can write as f prime of x equals the limit as h goes to 0. For this particular x we have plugged in, whatever this x value is, we're trying to find the instantaneous rate of change, in other words, the slope at this point. Divided by h. This is the definition for a derivative, definition for the slope, the rate of change. So this is the slope of the this is the slope of the tangent line, right? Remember, the tangent line is the point that's passing through, or it's the line that's passing through a given point. This is the slope of the tangent line at this particular point, x, f of x, whatever that may be. And so there we have it. There's our definition for the derivative. It is using this limit definition based on this idea of instantaneous rate of change. Delta y divided by delta x as delta x goes to 0. And so this is what we're going to use to calculate our derivatives. So, okay, that's all fine and good, but let's actually see an example so we know how to work through these problems. So, let me flip to the correct page for a moment. That is the wrong page. Here we go. Okay, there's two examples I want to do, and then we'll call it quits since we're getting towards the end of our time here. And I'll rewrite our definition because we're going to need that here in a moment. All right. So we have f prime of x, which is the derivative of the function f at a given point x, is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. And now that we have this definition, you can see why in the earlier sections we were practicing those questions with what does it mean to plug in x plus h, or x plus 2, x minus 3, whatever. You're going to have to know how to do that correctly in order to find these derivatives correctly. But you're going to see that. So as a first easy example, we have f of x is -2. This is our function, which, if we graph, that's the horizontal line at y equals -2. And we want to know the slope at the point 6, -2. So we're looking at where x equals 6. Now, based on this picture alone, you may already know what the slope is, but for the sake of practice, we can go ahead and apply this definition to find the slope via arithmetic here. So then the slope, f prime, at 6 is equal to the limit, as h goes to 0, of f of 6 plus h minus f of 6. So notice at this point, all I'm really doing is just copying what x is. I'm filling in the blanks, and then I'm going to go back and look at what f of x is and keep going. So this is the limit as h goes to 0. Now f of 6 plus h. If I plug 6 plus h into this equation, well, I just get 2. There's nothing I can plug in here. So I just have negative 2 minus another negative 2 divided by h. Well, negative is a double negative, so this is positive. Negative 2 plus 2, I'm really just looking at the limit as h goes to 0 of 0h. But now don't panic yet, because you may be thinking, well, if I plug in 0 for h, I have 0 divided by 0. That's bad. Don't worry about that. Whenever you're working through these problems, do not plug in h until the very end, after you've done as much simplifying as possible. So right now, h isn't 0. H is some variable. But if you think about it, what is 0 divided by h? What is 0 divided by x? Well, 0 divided by x, or 0 divided by h, is just 0. So the limit of 0, as h goes to 0, is 0. And you're done. And based on this graph, you may have already known that, yeah, this is a flat line. What is the slope of this line at any given point? Well, the slope of 0 steepness, so there's no steepness to this flat line here, there's no slope, so it's just 0. So anytime you see a horizontal line, you can automatically be thinking that means the slope is 0 everywhere. So that's a simple example. And then, just for the sake of showing you guys a little bit more tricky one, and we'll do this real quick in a minute or two, and then we'll call it quits. So for this last example, consider the function f of x is equal to 2 plus x squared at x equals 3. So the question is asking, what is the derivative at x equals 3? So we just plug and chug. Plug in our numbers and use this definition we already have up here. So this is the limit as h goes to 0 for f of 3 plus h minus f of 3 divided by h. So then we're going to plug it into our function. F of 3 plus h, that's going to be 2 plus 3 plus h plus quantity. And I've got 3 plus h in parentheses here because that x is squared. And then minus what I get when I plug in 3. So make sure you carry that negative here. So minus 2 minus 3 minus 3 squared, all divided by h. And just like before, don't worry about that h in the denominator. Let's clean up our numerator first. So right off the bat, we can already see we've got a 2 and a negative 2. So they're going to cancel each other out. We have a 3 minus 3. They're going to cancel each other out. Now we've got this h and this 3 plus h squared. So let's go ahead and square this guy so we can break it apart and see if we can cancel more. So 3 squared, and we still have an h over here. So we've got h plus 3 squared is 9. For our middle term, we're going to have 3h, but double it, so that's 6h plus h squared minus 3 squared is 9 divided by h. So this 9 and minus 9 are going to cancel. H plus 6h, that's 7h plus h squared divided by h. Well, now I'm at a point where I have an h here, an h here, and h here. I can divide this because they're separated by this plus sign. So what I really have is the limit as h goes to 0 for h divides 7h. We get 7 left over. H divides h squared, we're left with h. So now, as h goes to 0, we can just plug it in. This is 7 plus 0, or 7. And that is the slope of this equation at x equals 3. Or in other words, f prime of 3. So there you have it. So that's all the time we have for today. That covers everything I wanted for 2.2 A and B. Of course, we'll have Q&As later, and we can talk about this. So email me with any questions you may have, and by all means, we'll talk about this. If you feel like we covered this a little bit quickly or too fast, don't worry about that too much. Of course, we can talk about it, try to address your questions. You can always pause the video, rewatch the video, and there's also the lecture notes that I post that will show you these same step-by-steps if you would rather, maybe for whatever reason, maybe you can't read this super great. Then my notes I'll post online, you'll be able to see more clearly and maybe follow along with what's going on. So that wraps up what we have for today. So best of luck with your certified quizzes for Hawks Learning today, and I will see you all later.